yesterday you were given a huge overview of this whole topic about energy change or thermochemistry. It was a bit of an overwhelming lesson, and now we're going to start breaking it down into little pieces, and that's what we're going to do for this week. The first thing that we want to look at is enthalpy change, and one of the things we talked about is what enthalpy actually is. And enthalpy is our sum of the energy in a system. And a system is basically where our chemicals are, or our substance is. A closed system is one where those particles cannot leave and no particles can come in. And basically those are a couple of definitions we need. If we observe any chemical change occurring, there will be an enthalpy change. This means there will be a change in the amount of energy. Either that system, so chemicals and everything, will have to absorb energy for the chemical reaction or physical change to occur, or it will release energy, give it out to the environment. So, we call these endothermic and exothermic. Endothermic is where it absorbs energy, endo meaning inside, thermic heat, so it takes heat inside to react. Exothermic, exo outside, so it gives off the heat energy. We are expected to be able to describe this in everyday words. So an endothermic reaction, if you did it in a beaker in your hand, or a test tube in your hand, would start to feel colder. I put feels cold, that's a little bit simplistic. Feels colder. You would notice a temperature decrease because it's taking the water from its surroundings and putting it into making chemical bonds, for example. Okay. This is because it's absorbing energy, and we notice that most easily when heat energy is observed, and that turns into a temperature change for the surroundings. We say the enthalpy change is positive, so it goes from a low enthalpy or lower enthalpy here to a higher enthalpy here later in the reaction. I haven't labelled my x-axis because it's actually a thing called the reaction coefficient, so it's not actually time, but if everything was kept the same, like pressure and all that, it would be the same as time. But we don't label our x-axis. It's actually called the reaction coefficient. Alright? You don't really need to worry about it too much. Okay? You'll notice that the graph goes too high for a bit. It goes up to what we call this is actually an energy level, because this is in kilojoules per mole, and energy is in kilojoules, so it comes to an amount of energy. And here's where I'd like to remind you of some junior science and year 11 science, a thing called the collision theory. The collision theory states that for a chemical reaction to occur, particles must collide. They must collide in the correct orientation, and they must collide with enough energy to react successfully. You need three things to happen. That's the collision theory. So if you're not sure of the collision theory, do a bit of revision on that, because you need to know the three conditions required for a successful reaction to occur. Now, activation energy is that energy that those particles require to successfully collide. This is usually the energy required to break the bonds of the reagents, so that then new bonds can be made, the products. In an endothermic reaction, the products have more energy inside their chemical bonds than they had when they were reagents. This is why you get an enthalpy change that is positive. But it doesn't have to be a chemical change. It can be a physical change. Evaporation is a good example. When you're turning from a liquid to a gas, the bonding between the particles, not just between the atoms, between the particles, is being completely broken so that it turns into the gas phase. And it's got to get that energy from somewhere. And we all know, to boil or evaporate water, you have to heat it in a jug or on a stove or something like that. So that sort of makes sense. It's got to get that heat from somewhere. So that's endothermic. I'm going to explore it in a little bit more detail in a moment. Exothermic is the exact opposite. So everything that you would feel and see with an endothermic, the opposite is true of an exothermic reaction. If we were able to reverse an endothermic reaction, it would be an exothermic reaction. Good example, if I was to evaporate the water, it's endothermic. But then if I was to recondense it back into water, that's an exothermic process. I've got to take heat energy away for those particles to slow down and reform those bonds between them. Okay. So exothermic feels hotter. I should have put the relative term there. Feels hotter because that energy is being lost. And we don't lose energy, it's transformed. So it's transformed into heat energy. And the enthalpy change is negative. You'll again notice that it has to go up, the energy or enthalpy has to go up to the activation energy value before the reaction can occur. That's because even with an exothermic reaction, some bonds need to be broken first before it can start happening. So hopefully starting to get the idea that, and what I haven't put up here, is that when bonds are broken, it requires energy, absorbs energy. So this is the breaking of bonds. So conversely, what would be the exothermic version of that? Creating bonds, great, or making them. This will become really important probably at the start of next week when we do bond enthalpies or bond energies. Okay. Any questions on that before I flip the boards over?
How come with endothermic it feels cold yet the change in heat be positive?
Right, because it's absorbing that heat energy from the surroundings. So if it was your hand making I like using ice as a better example actually. If you get some ice in your hand, it feels cold. Would you agree with me there?
Yes.
Okay, what is happening to the ice because it's in your hand? Melting. So it's absorbing the heat energy out of your skin and some from the air to make it melt. So to break those bonds between the water particles so that it becomes liquid.
Yeah.
Okay, so that's why it feels cold, 'cause it's absorbing energy from you. It's actually taking some of your heat energy and taking it away for the reaction to occur. So that's why it feels cold. Does that sort of answer the question?
Yeah.
So if I had this reaction here, I wouldn't do this in my hand because the product's not being particularly nice for you. But if we did this one in our hand, it would feel really cold because the heat energy from your skin would be being absorbed to make these two solids combine.
Yeah, and with exothermic, if you had something hot in your hand, it'll be cooling down.
Fantastic. We wouldn't advise you do it, but if you put your hand over a jug, the steam, when it hits you, condenses and burns you. Okay, of course you wouldn't want to do that. The heat energy has to go somewhere. It goes into you because you're quite useful at absorbing heat energy. Okay, but again, wouldn't suggest doing it. Okay, moving on shortly to exploring the graphs a bit more.